Okay, hi. So the last topic that we did, the halting problem, was a very important topic. We showed that there are jobs that you can actually point to and say this job right here that are unsolvable. And we of course talked about some of the sort of idea, some of the concept ramifications of the halting problem. But my goodness, it's a long video. There's a lot in there. There's a lot to think about, and it kind of was a tough go in some sense. But so a person will be happy to hear that today's is a much shorter go. I think there's only three slides. So I think it's a little bit of an easier go. But it will do much the same thing. That is to say, what we're going to do today is show that problems are unsolvable, produce specific examples of problems that are unsolvable, describe how to do the homework kind of thing. But it is, in some sense, a more smoother process. The fact is that what we did last time, we need for today. So don't get me wrong, we had to do what we did last time, and it was important to understand all the ideas and everything. But it's still awful nice, isn't it, when you come up with a case that tends to be a little bit of an easier slide. That there's always a certain pleasure in that. So here we go, Rice's theorem. Okay, so when a person does the material from last time, you have these problems that we did at the end, you start saying to yourself, everything I write down, every time I write down a problem, it's unsolvable. Is it just every problem unsolvable? And the answer is pretty much. Every problem of a certain type is unsolvable. What type? Okay, well, that's what we're going to talk about today. Okay. So two computable functions have the same behavior. Phi sub b, I'm going to call that twiddles. Phi sub b twiddles, phi sub b hat. If they converge on the same inputs x, and when they do converge, they have the same outputs. That is to say, if they're the same function. If they have the same input-output behavior, including convergence or non-convergence. And then a set I of natural numbers is called an index set when for all indices e and e hat, if E is in I and phi E hat and phi E are related, twiddle each other, are related, by the way, described in the prior definition, then also E hat is in I. In other words, these index sets contain, if you have a function that has a certain behavior, let's say it outputs 7 on odd inputs and it outputs 9 on even inputs, then anytime you have an index for that function, it will be an I. An index set is a collection of indices. That's why it's called an index set. Index set is a collection of indices, but it has a property that if you describe to me a computable behavior, if you describe to me some phi e, and then you give me a different index for that same phi e, then that different index is in the set also. Okay, so it somehow collects together all the functions with the same behavior. Now you might have a collection of all the functions with the same behavior. They always output a 9, and a collection of functions with the same behavior. They always output a 7. And you put the two of those collections together to make a set. That's an index set too. But the point is that this respects same behavior is what an index set is about. Okay, and of course there are two examples there. It's the collection of indices of computable functions that have the property that phi ex equals 9. It's supposed to say for all x. I'm sorry. For all x, I apologize. For all x. And then the collection of indices e, where phi e of x is 2x or phi e of x is x plus 6, again for all x. And so there I've sort of conglomerated together two different behaviors, but any e that has the behavior that phi e is a doubler gets in there, and any e that has the behavior that phi e is a plus 6er also gets in there. And then the set of all e's, or the set of all indices where phi e of 1 holds. That's an index set. Okay. So Rice's theorem is that every index set, okay, so a non-trivial index set, every index set is not computable. By non-trivial, we mean not empty and not all the natural numbers. Every non-trivial index set is not computable. So when you had the sense, doing the homework from the halting problem material, when you had the sense that everything you write down is not computable, yeah, that was a good sense to have. Yeah. Anything that's about the behavior of a Turing machine, is not computable, is the kind of intuition here. So if I told you, for example, that I'm looking at all of the C programs where the third character is a capital T, you'd say that's a kind of a strange thing to do, but okay. And then I'd say, I'm wondering if that's computable. You'd say, of course it's computable. I just check the source code to see if it's a capital T. So, all right, okay. But that's not about the behavior. If instead I said to you, I'm looking at all of the C programs that square their input, okay, that's not computable. It's not possible to be given a Turing machine and say this is a square of yes or no. It's not possible to answer that question. Okay, so every index set, every set that is about the behavior of the computable functions, that's non-trivial, is not computable. Now, of course, we're going to go through the proof, of course we are, and then we're going to do a couple of examples. So the proof relies on what we've done before, so that we had to do what we did before, but the proof is actually, so you recognize the steps here, but the proof is actually reasonably straightforward, just kind of a lot of notation. Okay, so let's see. So you're given an index set. I'm going to choose a number so that phi e of e naught of y always diverges. So, so the Turing machine p sub e naught never halts for any input. Now, either e naught is in capital I or else e naught is not in capital I, so the proof breaks into two parts. We're not going to do the two parts because they're essentially the same. So I'm going to happen to do the second of the two parts the first of the two parts really is pretty much the same. It's a homework exercise. Okay, so we're working with an index such that the Turing machine with this index halts on no inputs. So we're going to assume that E naught is not in capital I, and since I is not empty, then there must be an E1 that is in capital I, and so we have these two indices E naught and E1. Because capital I is an index set, phi sub E naught and phi sub E1 can't have the same behavior. Because if you had the same behavior, you'd be all in the index set or else all out of the index. Okay, so since phi sub E1 does not have the same behavior as phi sub E naught, then it must halt on at least one input. All right, so now is the part where you recognize that it looks like the sort of stuff that we've been doing. So you consider the flow chart on the left below here. You note that E1 is not an input. It's hard-coded into the source. See the E1 right here? Right there. It's hard-coded into the source. But still, this is a perfectly writable program. By Church's thesis, there's a Turing machine with this behavior, so I'm going to let that Turing machine be PE. And again, deliberately trying to make it look like the videos that we saw last time. You apply the SMN theorem to parameterize x, so you result in a uniformly computable family of functions that you could write as P sub S of EX. And this uniformly computable collection of Turing machines correspond to the functions phi sub S of EX. We've constructed the machine on the right so that if phi x of x diverges, then phi s of ex it has the same behavior as phi e0, and so s of ex is not in I. And furthermore, if phi x of x converges, then phi. So if you never get through this box, then that's all there is to it. You know, you act like this function up here. But if you do get through the box, now there you are, you're acting like phi sub E1. So if you do get through the box, if phi x of x converges, then phi sub S of Ex acts like phi sub E1. And so S of Ex is in capital I. So because capital I is an index set, and so since E1 is in capital I, then S of Ex has to be in capital I too. So if I were mechanically solvable, if you could solve the question of membership in I, then we could effectively check whether S of Ex is in I. And we could solve the halting problem. So we can effectively check that S of Ex is in I, and we could tell whether you get through that box. I mean, you can't tell whether you get through that box, so there you go. Okay. Okay, so just like the arguments from last time, except that we generalize the arguments from last time. Okay, and then that leaves us solving a couple of problems. The difficulty with Rice's theorem, the thing that a person has to get used to with Rice's theorem, is that it goes by fast. So the problem of determining whether a given Turing machine halts on input 1, maybe you remember this problem from last time. So I'm going to solve this problem by Rice's theorem. So Rice's theorem says if you have an index set that's non-trivial, then it's unsolvable. So in order to show it's unsolvable, I'm going to produce a set. Well, it's written right there on the slide. I'm going to produce a set. I'm going to show it's non-trivial, that set is not the empty set, and that set is also not all the natural numbers, not the i's are not all the natural numbers. And then finally, I'm going to show it's an index set. So I have to go through the definition of an index set. So there's 3 things to do. 2 of them are very straightforward. Okay, let's give it a try. So before I do, I better write down I sub 0 here. I sub 0 is the set of all lowercase i's where program I halts on input I. Halts on input 1. I'm sorry, I misspoke. Okay, let me uncover there we go, uncover the paper. Okay, I need to show 3 things. I need to show that this is not empty, that this is not all the natural numbers, and finally that this is an index set. So we first show I0 is not empty. So in order to show that I0 is not empty, I need to show that there's at least one index in it. So I need to show that there is a Turing machine, P sub I, that halts on input 1. I mean, you know, it's trivial, but I'm going to write down anyway. So consider start, read, I think I can safely use the letter Y, and print. I like to print something, 42, and end. By Church's thesis, there's a Turing machine with this behavior. There is a Turing machine with this behavior. Okay, by Church's thesis, there's a Turing machine with this behavior, and it has an index. Which is a member of I0. Okay. So we next have to show that I0 is not all the natural numbers. So I'm going to write down a flow chart for a Turing machine that isn't, whose index is not in I0. So how about start, read Y, infinite loop. By Church's thesis, there's a Turing machine with that behavior. Its index is not a member of I0. Okay, now those 2 steps, a person can even say you should have just said it's clear. But anyway, those 2 steps were certainly not hard. All right, then the next step is to say that I0 is not, I0 is an index set. Finally, we show I0 as an index set. And you'll remember, I hope, what an index set is. We only saw it a minute or 2 ago, but of course a person could forget. So we have to assume E is a member of I0. and assume also that, whoops, phi E has the same behavior as phi E hat. Sorry about that. And I want to show down here, it will say something like, therefore E hat is a member of I naught. And that will make I naught an index set, and then I'll be done. Okay, well, if phi E hat has the same behavior as phi E, then phi E hat on 1 halts, because that's what phi E does. So E hat is a member of I naught. So I naught is an index set. So we're done. Okay? It goes by awful fast. Compared to the material from the last class, the danger here is that a person could person could miss it on the way by. Okay, I think instead of trying all three, I think I'm just going to try two, but let's have a whack at the second. The problem of determining whether a Turing machine ever outputs a 19. I1 is the set of all indices where there is an X, so that PI, Turing machine I, halts on X and outputs a 19. Okay, so what I got to do is I got to show three things. I got to show that I1 is not empty. I got to show that I1 is not all the natural numbers, and I got to show finally that I1 is an index set. Now you saw that the first two are pretty straightforward. I'm not willing to go to saying this is trivial and not writing anything at all, but I'm going to compress it a little bit from the last answer. But then the last thing is to show that I1 is an index set. Okay, okay, so let's do that. So I1 is the set of all i's. So we show I sub 1, which is the set of all i's where there is X, so phi I on X equals 19 is a non-trivial index set. Okay? Okay. So for the first two, I'll put them together on the same line so that I compress it a little bit. So to show that I1 is not empty, I just need to come up with some index for a Turing machine where the behavior of the Turing machine is that it halts for at least one input and outputs a 19. So I'm going to say this. Read X and print 19. And now that clearly has at least one X such that the output is 19. And over here I got to have a Turing machine, I'm going to sketch a Turing machine, whose behavior is such that it doesn't matter what X is. It never prints 19, so I'm going to print 18. Okay, so start. Read X. Print 18. And by Church's thesis, there's Turing machine for both of these. Each is computable by some Turing machine. The index of the first shows that I naught is not empty. The index of the first is a member of I naught. Oh, I1, forgive me, I1. So I1 is not empty. The index of the second is not a member of I1. So I1 is not all the natural numbers. Okay, so I1 is non-trivial. What remains to show is that I1 is an index set. We finish by showing I1 is an index set. You always do these the same way. You assume E is in I1, and that phi E has the same behavior as phi E1, phi E hat. Because phi E hat has the same behavior as phi E, we know that there must be an X. So because E is a member I1, there is an X with phi E X equals 19, then phi E hat X equals 19 also. That says phi E hat X equals 19 also, because they have the same behavior, so they do the same thing on X. So that means I1 is an index set, because if two functions have the same behavior, then they're both in. If two functions are both out, then they're both out. So, I1 is an index set. Okay, so we showed it's non-trivial. We show it's an index set, so that behavior is not computable. Okay, well, there's one more problem there, the problem of determining whether a Turing machine gives as output the square of its input. A slight change from last time. The problem of determining whether a given Turing machine gives as output the square of its input. Now, clearly, then, the difficulty is not the first paragraph about the non-trivial. The difficulty is not really the second paragraph about the index set. Clearly, the difficulty is in coming up with the solution for these, is writing down the correct index set, the correct capital I. So I'm just going to write down the correct capital I, and I'll leave the rest to you. So you have to determine whether a given Turing machine gives as output the square of its input. Okay, so I'm looking here for I2. It's the set of indices where for all x, Turing machine I on input x outputs x squared. Okay, you would show, it says for all x, Turing machine I on input x outputs x squared. You would show that that set is non-trivial, is not the empty set, does not contain all the natural numbers, and then you would show that it's an index set. So the three things, each of them proves to be, in most of these problems, proves to be very straightforward. And so showing that something is unsolvable by Rice's theorem, very much easier than showing it's unsolvable but with reference to the halting problem that we did last time. Now, of course, in order to prove Rice's theorem, we had to prove that we had to rely on the material that we did last time, so we had to do what we did last time. But nonetheless, it is the case that Rice's theorem, here, let me get back to the statement. There we go. That Rice's theorem is often a much smoother or easier way to show that something is unsolvable. Okay, all right, very good. Much easier. This video much easier than the last video.